This is a video for Edexcel Further Pure 1, Vectors Section 1.7, Volume of Parallelepiped and Tetrahedron. This diagram is of a parallelepiped, which is basically a box which has been pushed over, so that opposite sides are congruent parallelograms. In this case, it's been defined by the vectors along the sides A, B and C. Now we know that the volume of this sort of object is equal to the area of the base, which is shaded, multiplied by the perpendicular height h. From work that we've done previously, we know we can calculate the area of the base by looking at the cross product of the two vectors forming the base, so b cross c, and then taking the modulus of that, and that will give us the area. H, if we look at the triangle up here, then taking the length of A and cosine theta gives us h. So h is equal to the modulus of A cosine of theta. Therefore, putting those two things together, we've got that the volume is equal to the modulus of B cross C multiplied by the modulus of A cosine theta. But if you look at that, then B cross C is a vector in the direction of h, the perpendicular height, and then we've got the length of that multiplied by the length of another vector, cosine of the angle between them. So this is a dot product. In other words, we've got the dot product of A together with the vector product of B cross C, and we're finding the modulus of that. So that we have that the volume of the parallelepiped is the size of the scalar triple product A dot B cross C. We need that final modulus because the scalar triple product can be positive and negative, and we want obviously for the volume to have a positive value. So looking at just through that again, the area of the base is the length of B cross C, and then we can combine that with the perpendicular height to give us this formula here for the volume of the parallelepiped as being the size of the scalar triple product. Now in your formula sheets, the scalar triple product is given, so we have a formula for A dot B cross C. However, you're not told that this is equivalent to the volume of the parallelepiped formed by the three sides, so you need to remember that fact. However, in questions quite often what happens is not that you're expected to use this formula straight away, but it works through this method by getting you to calculate the cross product of two vectors and then the dot product between that answer and a third, and interpreting that as being the volume. So that's basically what I'm going to do in the question that follows. So this question defines the parallelepiped by giving us the coordinates of four of the corners, A, B, C and E. And obviously from those four coordinates we can calculate vectors AB, BC and AE. Once we've got those vectors, we can find the vector product AB cross with BC, and then the dot product of that with AE. So first of all, what I'd like you to do is to find AB, BC and form the cross product of those, and then when you've done that, come back to the next slide which will go through the solution. Well, hopefully you've done that and got the following solution. AB cross BC, well AB is the position vector of B minus the position vector of A, and BC is position vector C minus A. and that gives us these two vectors, and when we form the cross product you get the vector 6, 6, 0. What I'd like you now to do is to calculate AE and to form the dot product of AE with this answer here. So to find AE dotted with 6, 6, 0. And the size of that will be equal to the volume of the parallelepiped. So pause the video again and complete the exercise. Well, here we have the full solution where we calculated AB cross BC here as being 6, 6, 0. AE turns out to be, well, this is position vector E minus position vector of A, and that turns out to be 0, 1, 1. So when we form the dot product we get 6, and hence the volume of the parallelepiped is 6. Now, had a question simply asked us to work out the volume, then we could do that by using the vectors AB, BC and AE and calculating the scalar triple product directly. So let's look at that. AE 0, 1, 1, AB 1, negative 1, negative 2, and BC negative 3, 3, 0. So the scalar triple product is given by the determinant of made up of the values in those vectors written along the rows. So AE 0, 1, 1, AB 1, negative 1, negative 2, and BC negative 3, 3, 0. This is a 3 by 3 determinant that we need to find, and to get that we take 0 multiplied by the little 2 by 2 determinant coming from here, so it's 0 multiplied by negative 1, negative 2, 3, 0, and then minus 1 multiplied by the determinant from the first and the third column, so that's 1, negative 2, negative 3, and 0, and finally 1 multiplied by the determinant from the first two columns, 1, negative 1, negative 3, and 3. And here that's written out nice neatly. Well, obviously the first part there is 0 because of the 0 in front. The second part we have negative of then 0 minus 6, so negative of negative 6 is 6. And finally we've got here 3 minus 3, so that gives us 0 again, giving a final answer of 6 as before. Now remember that the scalar triple product could give you a negative value, and then we would need to take the modulus of that to give us the volume. So we're saying that the volume is equal to the AE dotted with AB, BC, so the scalar triple product and the size of that, and that's going to be true for any parallelepiped. I now want to turn attention from this to a tetrahedron. This diagram shows a tetrahedron, and you can see the similarities between this and the parallelepiped. Of course, this time we've got the volume is going to be 1/3 the area of the base multiplied by the perpendicular height, and the area of the base is a triangle, so therefore it's going to be 1/2 of B cross C this time. So we get 1/3 multiplied by 1/2, B cross C being the third area of the base. So looking at that written out, you see that the rest of the argument is very, very similar to that for the parallelepiped. And we end up with, because of that 1/3 in the volume formula and the 1/2 being a triangle rather than a parallelogram, gives us 1/6 of the size of the scalar triple product. So for a tetrahedron, the volume is 1/6, and then mod of the scalar triple product A dot B cross C. So in this example we have got three non-coplanar sides of a tetrahedron given by the vectors A, B and C. So these are the vectors that we need. The first thing then we need to calculate is the scalar triple product A dot B cross C, which we can get by using the determinant of the 3x3 matrix made up by rows using the elements of A, B and C. So the first row will be 1, 2 and 0 using A. The second row using B will be 2, -1, -1, and the third one -1, 4 and 6. Calculating that then, the usual method for a 3x3 determinant, it's 1 multiplied by the 2x2 determinant from the bottom right hand corner, -1, -1, 4 and 6, then minus 2 times the little 2x2 made up of the first and the third columns, so 2, -1, -1 and 6. The third one will be 0, coming from that element in the top right there, so we can just write that down as being 0. If we calculate this, the first 2x2 determinant is -6 minus -4. Then we've got minus 2 times and 12 minus 1. And that calculates to be -24. Hence the volume that we need for the tetrahedron is going to be 1/6 of the modulus of -24, which of course is equal to 4. So in summary for this video, the volume of a parallelepiped is given by the size of the scalar triple product A dot B cross C. The volume of a tetrahedron is given by 1/6 of the size of the scalar triple product formed by the sides of the tetrahedron. Well, that concludes this video and indeed concludes the whole section of videos for vectors.